So the topic of my talk today is around reconfigurable intelligent surfaces or smart surfaces, whatever you name them. Before going into detail about this exciting area, I will briefly talk about University of Glasgow, then some challenges around 6G, and then I'll come to the topic of reconfigurable intelligent surfaces. So I'm Qammer Abbasi, and I am currently professor in University of Glasgow, and also I am a policy advisor for UK Government Department for Science, Innovation and Technology, and advice around future telecom. So if you don't know where University of Glasgow is, it is somewhere in the United Kingdom. It's one of the fourth oldest university in English-speaking world, established in 1451. As you can see, it is in the north of United Kingdom, and it is established after Oxford, Cambridge, and St. Andrews. And University of Glasgow is home to various Nobel laureates and home to various world-leading inventors, including Lord Kelvin. I'm sure everyone has heard about him, that he invented the unit for temperature, which we all study in our school and colleges, Kelvin. But many, I'm sure, but not many of you know that he is the person who laid down the first transatlantic cable between America, North America, and UK. So he is one of the pioneer for telecommunication as well. And this year we celebrated the 200th bicentenary for Lord Kelvin in University of Glasgow, and also John Logie Baird, who made the television, was University of Glasgow alumni. 2021 Nobel laureate for chemistry, was also University of Glasgow alumni, and University of Glasgow is Scottish University of the Year for 2024, and it's ranked top 100 in the world, and it is home to the Scotland Innovation Centre for Sensing, Imaging and Internet, and also National Scotland 5G Centre. And I'm directing this center called Communication Sensing and Imaging Hub, which is home to Scotland 5G Centre Urban Testbed. And also we work, and also the recently funded UK government 6G hubs. It's part of one of the hub, and we have around 140 researchers working from device level up to application layer for various applications, including healthcare, agri-tech, robotics, so on and so forth. So before making the case for 6G and reconfigurable intelligent surfaces, I need to take you a bit back. I'm sure many of you who are on this call were not born when 1G came in 1980s. Even I was not born at that time. But the key here is that every 10 years, we have a new generation of mobile communication coming, and each generation is better than previous generation in terms of features and data rates. But the real revolution came when 5G evolved, because we started talking beyond mobile connectivity. We started talking about connectivity of an ecosystem. And then when we started talking about 6G a few years back, we started talking about 6G will be better than 5G, will have some enhanced feature, including joint sensing and communication. We'll talk about that, because I need to make a case for 6G, why we need 6G, and then the things will flow automatically. So we have the demand for digital communication or digital services demand increasing day by day. These are stats for April 2024, where we have around 67% of the global population using internet, and an average user is spending 6 to 7 hours a day on using internet. And of course, it depends on the area where it is being used, and at some places it's even used more. So one of the challenge actually came for 5G was that I was in Mobile World Congress last year, and for the first time since inception of mobile communication, the return on investment for the operators and vendor was not huge. And the point or the reason for that low return on investment is acceptability of 5G. I'm sure many of you have heard that in South Korea they have recalled 5G because I'm sure many of us know that there are so many things whichever people talk about that 5G can do this can be done by 4G as well. And the problem comes here is that do we really need 5G? Because whatever 5G is doing, we can do by 4G as well. And the problem, again, as I mentioned, is that the demand for 5G or the use cases which need 5G is not huge, uh, which led to low return on investment. And the reason, or I would say, one of the challenge which led to this problem is that in past years, whenever we want to make a network, we start by setting KPIs that these are the KPIs, let's make a network. And once network is being made, then we start looking for use cases. And this is what happened in 5G. KPIs were being set, 5G was being deployed, and then we were unable to find large number of use cases which can enable 5G or which will be enabled by 5G, which led to various issues which I mentioned around return on investment and revoking of 5G in South Korea. So when discussions around 6G started happening, the first thing was that people started talking about, oh, what will be the KPIs of 6G? Of course, it will be better than 5G in terms of peak data rate, battery lifetime, high resolution, energy efficiency. But we said that, okay, let us think differently because this will not work like what is happening to 5G. So we said that instead of talking about KPIs, let's talk about a use case or use cases which need 6G and what are the requirements, and then we start making the network. Means instead of using bottom-up approach, we started with a top-down, top-down approach. So now let's talk about a use case. Our use cases which need 6G and what are their requirements, and then we start talking about 6G. So we came up with a very interesting use case which we call it Internet of Senses. We all know that we humans have 5 senses, right? But some of the special humans might have 6 senses as well, but normal people have 5 senses. So up to now we are able to transport at least 2.5 or 3 senses from point A to point B, which includes hearing, of course, with mobile phone audio, vision by using mobile phone video call, touch. You have seen so much robotics around us, so haptic feedback, which is basically touch. But we are unable to transport taste and smell from point A to point B. And I'm sure many of us have seen this holographic communication. Holographic communication is when we can teleport a user from point A to point B. But imagine, can we teleport a human from point A to point B with all the 5 senses? This will create a real senses-based holograph, right? So if we can teleport all 5 senses from point A to point B, then we can have something which is amazing. But this needs something very unique which 5G cannot do. For example, if I want to teleport a touch from point A to point B, 1 inch square meter of hand needs around 1 gigabits per second of data. And imagine if I want to teleport complete palm of hand, a palm, and if I want to teleport different textures, we need humongous amount of data. And imagine if we want to teleport all 5 senses together from point A to point B in close to real time, we need ultra low latency, ultra high throughput, and very large bandwidth, which is not possible by 5G. So see, I made a case that there is some use case which needs something which 5G cannot do. And that is 6G. And the elements of 6G, it's under discussion, but consensus among researchers is that it will be ubiquitous, it will be ultra high in terms of precision, ultra low energy, ultra massive connectivity to enable various other use cases, including bullet trains, hyperloops, smart factories, and so on and so forth. So I made the case that we need a new network. There are some use cases which needs that. 5G cannot do that. So that is 6G. And in our hub, we are working on various technologies to enable 6G, which includes antennas, reconfigurable intelligent surfaces, quantum, so on and so forth. So I'll briefly touch antennas and mostly focus on reconfigurable intelligent surfaces because that is the focus of the talk. And the prospective band, which is under discussion for 6G, is terahertz because it enables this peak data rates, which we need for the use cases I just mentioned, including sense-based holographic communication, extended reality, precision, telemedicine control, ultra low latency up to 0.1 millisecond. So terahertz is a band which can help us to envision 6G. And whenever there's a technology, it comes with challenges. And terahertz has its own challenges, including atmospheric absorption. Terahertz has a frequency selective behavior and it's sensitive to fog, and so forth. And it's very much sensitive to water contents. And second thing is skin depth. As we move higher in frequency, the skin depth reduces. And same is the challenge for terahertz as well. And at terahertz frequencies, the conventional materials which we use, including copper, aluminium, they does not work. So we need to think of some new materials. So in order to overcome some of these challenges, in our hub, we are trying to develop new antennas because this topic is linked to reconfigurable intelligent surfaces. So I want to spend 2-3 minutes to talk about this. So we know that antennas are ears and eyes of a wireless communication system. And as I mentioned that at terahertz frequencies, conventional materials will not work. So we started looking at some 2D materials, including graphene, perovskite, HBN, to develop these antennas because these 2D materials have surface plasmon phenomena at terahertz, which help us to overcome the challenges I just mentioned. And in our hub, we have developed world first various terahertz antennas based on combination of material, including graphene, aluminium, titanium, both flexible and non-flexible. And the reason we were able to achieve and fabricate these antennas is because we have state-of-the-art facilities where we have James Watt Nano Fabrication Center, a 1400 meter square clean room, and measurement and characterization capabilities from 10 megahertz up to 1.1 terahertz, which helped us to fabricate and measure these antennas. So one of the example I want to give you is this planar inverted cone antenna, which is 1x4 element array made up of gold with a total dimensions of 1000 to 2000 microns. And it is being fabricated through a standard procedure in James Watt Nanofabrication Center using electrobeam lithography, where we have used ground signal ground configuration, and the pitch or this gap was in few microns. So we measured this by using a 25 micron meter on probe measurement pin, where we were able to achieve a very good agreement between measurement and simulation. You can see these are S parameters. Of course, at such frequencies, very high frequencies, we have some kind of measurement errors which we cannot control, and the realized gain was around 14 dBi. And radiation pattern was close to omnidirectional. So let's come to the main topic, which is reconfigurable intelligent surfaces or intelligent reflective surfaces, whatever you name it. And I'm assuming that some of the people might not have heard this, are not very well aware of this topic. So I'll try to explain briefly what these reconfigurable intelligent surfaces are. So this is Hunterian Museum in University of Glasgow. Imagine we want to provide coverage to a user. She's using a mobile phone while sitting in Hunterian Museum. So whatever signal is reaching to her, there is no direct path. We have reflection, diffraction, and scattering. So ultimately, whatever signal is reaching to her has either constructive or destructive interference, ultimately leading to reduction in quality of service. But imagine if we have something which can focus the beam on a user, ultimately it will improve quality of service. And trust me, this is nothing new. This work has been done hundreds of years ago, where our ancestors were using mirrors to control the light. When there was no electricity, they were using mirrors to control light. And we are using these reconfigurable intelligent surfaces to control electromagnetic waves. So these are mirrors to electromagnetic waves so that we can control them. So these are called reconfigurable intelligent surfaces, whatever name you want to give, meta surfaces, or so on. And they have applications in all domain of life, ranging from coverage enhancement, airports, train stations, healthcare. This is one of the topic of my talk as well, where we will be talking about their application in healthcare. So in next 30-40 minutes, I will be talking about some of the designs we did for these reconfigurable intelligent surfaces, their role in communication, both in indoor and outdoor, and then how we can use these surfaces for sensing, which is I mentioned about healthcare use case, then for localization, and then most important aspect for 6G, which is joint sensing and communication. I will be showing you some of world first demonstrations on this, and then Open RAN with RIS, another use case. So in University of Glasgow, we have developed various large-scale test beds, 1-bit horizontally polarized, 3-bit vertically polarized, a 1-bit dual polarized at sub 6 gigahertz, X-band RIS, Wi-Fi 5.2 gigahertz, millimeter wave, transparent RIS. So I'll be showing you some of them. So the first test bed is 1-bit reconfigurable intelligent surface. When I say 1-bit, it means it can change the phase of incoming signal by 180 degree. So how you design these surfaces is that you design a meta cell or a meta unit. It's patch antenna divided in 2 parts, where we have a switching element at the back to avoid electromagnetic interference. You make one meta cell and then you replicate it to make a tile. And the idea to make a tile is that if you have one tile, you can just simply replicate that tile to make this structure as big as you like, any shape you like, cascaded, parallel, so on and so forth. So our this 1-bit RIS had each tile had 256 elements. So we and each unit cell was controlled by a pin diode. So ultimately we had 16 tiles connected together to make a large structure which had 4096 unit cells, where each unit cell was controlled by pin diode at the back, and these shift registers which were basically trying to give the configuration to these unit cells, and it was controlled by a Raspberry Pi. So as I mentioned, the center frequency was sub 6 gigahertz, means 3.75 gigahertz, and the total size of this RIS was 1.4 cross 1.4 meter, and the switching speed was around 20 millisecond. One thing to remember is the power. So the total power consumption by this structure was around 15 watt. So because we were able to control each unit cell, so this RIS had both near field and far field performance. The near field performance was within 5 meter and far field performance was up to 50 meter. And the second design was a 3-bit RIS, which was column control and vertically polarized. The process was similar. We started with a meta cell. It had 3 pin diodes. And when I say 3 pin diodes, it means it had 2 raised to the power 3 states, which is 8 means you can change the phase of incoming signal by phase difference of 45 degree, 45, 90, minus 45, minus 90. So in total 8 states. And to simplify our structure, we made it column control. Instead of controlling each unit cell, we were controlling each column by 3 pin diodes. So process was similar. We made a tile, we replicated those tiles, and it was column control because each column was controlled by 3 pin diodes. And the reason for doing this was to reduce complexity. So it had again Raspberry Pi to control the states. So in this case, we had 6 tiles in total. So the total size was 1 meter cross 0.7 meter. And the total unit cells were around 2304. So this is the multi-bit RIS prototype. You can see power supply, Raspberry Pi, FPGA to control configuration. Now we have made our RIS. Now we want to check whether they actually work. So simulation measurement were in agreement. We fabricated it. And the reason was, you remember, we want to get coverage enhancement, means we want to have some gain. So we took our RIS to anechoic chamber, used horn antennas, and looked at the phases and amplitude. And you can see that there was a great agreement between simulation and anechoic chamber measurement. For phases, there were some kind of anomalies in amplitude, and the reason was there was some of the rupture pin diodes which we fixed. So in anechoic chamber, it was working. Now we want to see in real environment, does this RIS really give us coverage enhancement, which we were talking about? So we started with an indoor trials. So what we did, we used 3 different indoor scenarios. Corridor scenario, where you can see we have a transmitter here, a receiver placed at different location, where transmitter receiver cannot see each other, and RIS was acting somewhere in the middle. The second was lobby area, which is another common scenario. You can see there were some scenarios where there was no line of sight. The third was multi-floor scenario, where transmitter and receiver cannot see each other, and also they are on different floors. Of course, the measurement campaign was very thorough, but I'll jump to the results directly, that we were able to achieve an average signal improvement of around 20 dB, whereas in some cases it was 40 dB as well. But remember another thing, that we are using here horn antennas, which are directional antennas. But this proved our point that, okay, these RIS are working in an indoor environment and they are giving coverage enhancement. We were very excited. We talked to our industrial partner. We told them that, look, this RIS is working in an indoor environment, giving a great coverage enhancement. They asked us, what is the power consumption? And I don't know if some of you remember, the power consumption was 15 watt, which was very high. And they said to us, oh, this is not acceptable because this power consumption is very high. And as a researcher, we got demotivated. We went back because we were super excited. So we started thinking that how we can solve this issue. So if you remember, we were using pin diode, so which was consuming all the power. And pin diode works in forward bias. So we came up with an interesting idea that if we can use varactor diodes, because varactor diodes work in reverse bias, ultimately there is no current and ultimately there is minimal power consumption. So we came up with a new design where the process was similar. We designed a meta cell or a unit cell, but this time the switching element was varactor diode and power consumption was reduced from watts to few milliwatts. So we made 4 tiles in this case, as you can see. And another benefit we got from varactor based RIS was that we are, once in the previous case you make a RIS, you cannot change the center frequency. But as you know that if you change voltage in varactor, you can change the capacitance. So ultimately, we can change the center frequency as well. And another thing this RIS was able to do was that it was dual polarized, that it has both horizontal and vertical polarization, because we don't know which polarization signal is coming. So this was the requirement that it needs to be dual polarized. So we basically designed a new RIS which was dual polarized, where we can change the center frequency as well. And another thing we were able to do was beam steering. So we did in simulation and showed that we can do the beam steering from 0 to 180 degree. For a fixed incidence angle, we were looking at the received signals and we were able to steer the beam from 0 to 180 degree, but this was in simulation. So we went to University of Southern California with Professor Molish group, where we used their channel sounders to do measurements for beam steering, and you can see that there's a great agreement between simulation and measurement, where we demonstrated that we can do beam steering with our new design as well. So I think this, then the next thing was, if you remember, I mentioned that one of the key feature for 6G is its joint sensing and communication. Joint sensing and communication means that we are using same frequency band for doing communication, which we already do, but sensing as well. So we demonstrated that in X band from 8 to 12 gigahertz. So for that, we need to make a RIS as well. So what we did, we designed an X band RIS. Again, process was similar. It was 1 bit. We designed a unit cell. It was pin diode based, where the phase difference was 180 degree plus minus 20 degree. And this was the phase distribution for beam steering of 0 to 40 degree, this RIS structure. And it was giving us a gain of greater than 18 dBi at plus minus 40 degree. And at a both side, it was giving us around 20 dBi gain. And this structure, if you remember, in our previous design, the switching speed was around 20 millisecond, which was very high. And we have modified our control circuitry, which you can see was mostly on the front side. And ultimately, the beam switching speed was reduced to 0.5 microsecond. And it had 4 tiles with a single tile with a dimension of 25 cross 25 centimeter. And these are the measurement results in an anechoic chamber where we were getting phase difference of 180 degree plus minus 20 degree as per requirement in the complete band 9 to 10 gigahertz. Then we try to make RIS at millimeter wave band as well at N257 FR2 band, where we had an angular stability of up to 30 degree, and it was vertically polarized, and the reflection loss was less than 2.1 dB, and it was 1 bit, means we had a phase difference of 180 degree, as you can see. And it had an angular stability of up to 30 degree in both azimuth and elevation plane. Last but not least, we made a transparent static RIS, and it was static because we were not able to do switching, which is, of course, work in progress, but this was static. We were using, the idea was that it on a window, so we were using silver nanowires, and it was giving us a reflection loss less than 2.5 dB at 25 gigahertz, and it was 1 bit, and the beam steering was again from 0 to 40 degree with a minimum gain of 20 dBi. So, uh, so the thing is that we have made various restructures, but we didn't ignore some of the challenging parts of this reconfigurable intelligent surfaces design, which is mostly ignored by some of the researchers, which is around mutual coupling and electromagnetic interference. So, these unit cells, if you remember, they are closely packed to each other. So they have both mutual coupling and electromagnetic interference. So we looked at both fundamental issues as well, and we are still investigating. And the key here is that if you look here, that these switching elements, right? We have switching elements which introduces capacitance. So when we have these switching element in, if you look at this X4 and Y4, basically X4 and X4, here we have a phase difference of 90 and minus 90 degree. Okay, when there is, we consider no mutual coupling. But as soon as we consider mutual coupling, what happens is that the capacitance value changes, and ultimately, because of that, the phase changes as well. And also, if we consider no electromagnetic interference, and if we consider electromagnetic interference, there is a big change on a data rate. So if we consider both EMI and mutual coupling, because of change in these phases, as I told you, because of mutual coupling and because of EMI, the peak data rate changes humongously. If you look at this black curve, this is with EMI and with mutual coupling. And this red one is without EMI, which is around 110. If we look at 30 users, it is around 120 megabits per second. And if we consider both mutual coupling and electromagnetic interference, it reduces to 70, which is huge. So what we try to do is that we have algorithmic designers as well, algorithms. So what we have done is that we have basically considered an iterative algorithm where we were using water filling to allocate power to various users with and without EMI. And this algorithm, what it was doing, that it was basically giving more power allocation to users where we have a less impact on mutual coupling and EMI. So it was basically doing water filling on power in a way that we were able to compensate for EMI and mutual coupling. And ultimately, it was giving us a result in terms of data rate, which was very close to what when we were not considering any EMI. So this is a video demo which will show about our RIS, which I'm talking. Let's see if it works. And it will show you a video streaming demonstration over an intelligent reflective surface. This intelligent reflective surface have been developed in University of. So what we are trying to do is we want to transmit a video from point A to point B where horn antennas were connected with USRPs and they were unable to see. And this RIS was acting as you can see in the screen on the right hand side. At this stage, our IRS is not working and the signal quality is so low. So now we will configure our IRS. As signal quality is so low, video is not being streamed. So as soon as we have configured our IRS, you can see that signal strength is going up and then video streaming will start. And our signal quality is increased by around 25 dB by using the. This is another video demonstration for our beam scanning RIS. Intelligent reflective surface with around 4,000 elements, which is scanning the beam in complete 360-degree in free space. As you can see that wave is rotating from 0 degree to 90 degree and then 180 to 270 and then coming back to 360 degree. So here we have done work for risk coverage enhancement in an indoor scenario. So I was delivering a talk in one of the conferences and someone said to me that, oh, your RIS will not work in real environment because you are using directional antennas. If you remember, I told you we were using horn antennas in all our trials. And in reality, means in a network, they are not directional, right? Like a horn antenna. So somebody said to me, and that always make us think and make me think as well that, okay, let us see if it works in real environment or not. So we did world first operator-based trial. The details for paper are down here. So what we did that we deployed our RIS in an industrial park in UK, which is British Telecom Network. So we use their mast, the receiver antennas to do trials. So this is where mast is. We placed our RIS in two zones, zone A, zone B. So this is zone A, zone B. And if you see that we have in zone A, RIS placed here and then 3 receiver location. Zone B, RIS placed here and 3 receiver locations. So, of course, it's needless to say that it took us months to plan the experiment, then doing all the calibration and using all kind of preliminary tests. But what is important is the results. So this is zone A, RIS placed here and 3 receiver locations. Location 1, you can see that when RIS was not playing any role, this is the reference signal. When we optimized it, there is a gain. When we move to location 2, there's a gain enhancement of around 10 dB, location 3 around 13 dB, and if we combine all these three locations, this is a gain enhancement from around 5 to 15 dB. And if we look at a transmit power of 33.6 dBm, we were getting a capacity enhancement of around 50%, which proves our point that this RIS works in an outdoor real environment as well. And as a researcher, we got excited. We all get excited when we get results what we want. But when we looked at zone B, there was almost no gain improvement, right? And we got depressed. We started looking at what is the reason, and we came to know that these receiver locations were so close to the mast that RIS was not playing any role, and there was direct communication which led to no further signal enhancement. So we looked at various other scenarios where we tilted RIS in various angles to see the interference issues, and this is still work in progress which we are looking at. But the key findings were that RIS aided MIMO can be a game changer for future communication, where we can get a gain enhancement of around 10 to 15 dB and a potential capacity enhancement of over 50% for several user location with only 10 milliwatt power consumption. So up to here, I made a case, I proved that RIS has a great role in communication. So the next is RIS for sensing. And remember, I talked about joint sensing and communication. So I'll show that later on. So the key here is that we are moving from doctor-centric healthcare to patient-centric healthcare. It means that I want to control my health myself instead of going to doctor who asks me some questions and then prescribe me something. And with these new wearable and non-wearable devices, we have control of our health ourselves. So the idea is that we are going to have smart homes in future where we have various kind of sensors, including wearable, implant, RFID, environmental sensors, point of care devices, nanoscale devices, and most importantly, contactless sensing. And these all sensing modalities will work together, and this multimodal information will be sent to cloud, where machine learning and deep learning will be performed on a data to ultimately do proactive healthcare detection. But in interest of this topic, I'll be talking only about contactless sensing. And what is contactless sensing? We have these ambient radio frequency signals around us, mobile Wi-Fi signals. Can we use these signals to monitor someone's health, which includes their vitals, their activity patterns, because gait is linked to various kind of disease. So the challenge with contactless sensing was threefold. Number one, for contactless sensing to work, the subject needs to be in line of sight between transmitter and receiver. Number two, because the radio frequency signals are ambient, so you do not have high resolution. Number three, if we have multiple people in a room, or if we have someone walking and we want to localize it, we were unable to do it. But I'm sure you guessed it, what I want to say, that what we have done is that we use these reconfigurable intelligent surfaces to control the beam. So ultimately, you can monitor people in non-line of sight scenario. You can localize the target. You can focus the beam on a user to enhance resolution as well. So we published this paper in Nature where we demonstrated that how we can use these reconfigurable intelligent surfaces to overcome the challenges of this contactless sensing. So to prove that, we designed various indoor experiments. So this is a corridor scenario where transmitter and receiver were unable to see each other. The user was performing some activities here. RIS was acting somewhere in the middle. We used various scenarios, including corridor, multi-floor scenario. Transmitter is somewhere in first floor, receiver in ground floor, and user was somewhere in the middle, performing activities close to RIS. And results were what matters. That when IRS was off, user was performing three kind of activities. We were unable to detect any activity, but as soon as we have turned on RIS, we were able to detect with an accuracy of 100%. And this was work being done 2 years ago. We have done so many other things in this domain as well. And another interesting thing we did was how we can use these surfaces and contactless sensing to enhance future hearing aid devices. So one of the challenge with hearing aid devices is cocktail effect. Basically, what is cocktail effect? That these hearing aid devices, they have a noise threshold which is not tuned to various environment, and which led to so much pain to hearing impaired people. So they do not like to wear these hearing aid devices. And what we thought was that, can we make these hearing aid devices intelligent, inspired by brain? For example, when I'm talking, your brain is interpreting information not only based on my audio, it's looking at the slides, it's looking at the text, and maybe my facial expression, combining all that information and then converting it to the text are useful information. So we thought of the same principle that, okay, let's make a hearing aid device which is intelligent, which takes multimodal information, including audio signals, lip movement, facial expression, so on and so forth. So Google had glasses which can read the lip movement by using camera. But if you remember, in pandemic, we came up with a new challenge that everyone was wearing a mask. So ultimately, that solution failed. But as we know that radio waves can penetrate inside the clothing, so ultimately we were able to read the lip movement with uh, where we started with vowels and then later on with sentences, but this paper was based on vowels. We were able to detect vowels with an accuracy of more than 90% by using this contactless sensing technique. Later on, we have embedded these meta surfaces in the mask, and we were able to study sentences as well. And then, if you remember, I told you that with previous contactless sensing technique, you are able to measure anything when it is happening between transmitter and receiver, right? This is the user. But what we demonstrated that with these reconfigurable intelligent surfaces, you can detect in non-line of sight scenario as well. So what we demonstrated that we measured the vital, which was heart rate and breathing rate for the user in non-line of sight scenario by using these reconfigurable intelligent surfaces. We use off-the-shelf breathing and heart rate sensors, which is vernier go belt for breathing and bipolar sensor for heart rate to measure breathing rate and heart rate with an error of only 1%. We have a patent and paper for this as well. And then another thing we did was that how we can use these reconfigurable intelligent surfaces to reduce E-field exposure. So we used a phantom where we were using a probe-based measurement to demonstrate that by using RIS, you can reduce the uplink power. Ultimately, you will be reducing the E-field exposure. And then we use these surfaces for doing brain-computer communication as well, where we were using these transmitting and receiving surfaces to transmit the BCI from operator A to operator B, and these papers are published as well. So this was RIS for sensing, and the last two bits are, I know I have few minutes left, but last two bits are RIS for localization and joint sensing and communication. So the benefit of localization are humongous. We know that GPS does not work indoor, right? So, but a localization has benefits for asset tracking, navigation and wayfinding, manufacturing and warehouse, indoor positioning, so on and so forth. So what we have demonstrated is that we can use these RIS surfaces for doing localization inside. So what we did, that we designed an experiment in an indoor environment. We have published this in Nature Communication Engineering as well. So what we did, that we have used an indoor scenario where we divided the indoor region in 9 different locations. We used USRP based transmitter and receiver, where we had horn antennas, of course, and then we had RIS, which was basically helping us in this localization because we were focusing the beam, and we gigahertz, and we were to localize the target with an accuracy of more than 85% by using our RIS aided communication. Now, the next bit is this joint sensing and communication, which is one of the key feature of 6G, called integrated sensing and communication as well. And its feature are humongous, ranging from spectrum efficiency to cost saving, enhanced performance, so on and so forth. So what we demonstrated was basically that how we can use our custom built radar to sense the activities and vitals for the users, and at the same time doing the communication as well. So we demonstrated this with and without RIS both, but here I'm only showing this joint sensing and communication without RIS because the other work is still in progress. So one of our student developed a bespoke SDR based radar, which had a bandwidth of 1 gigahertz working at a center frequency of 9.5 gigahertz. And if you remember, we designed the RIS at same center frequency and bandwidth as well. It had 1 transmitter channel and 2 receiver channels. The users were wearing off the shelf breathing and heart rate sensor for a baseline measurement, which I just mentioned earlier, that Vernier sensor for respiration and heart rate sensor as well. And I think this video demonstration will clarify everything what I meant to say. Oh, okay. 1 second. Okay. So this is, we are demonstrating vitals for moving targets, basically, which is both sensing and communication. If you see here, this is the read range measurement, and this is the heart rate and breathing rate spectrograms. And here, if you see, users are static. As soon as the users will start moving, we are communicating this information through read range, and we are already sensing their heart rate and breathing rate, which we are still processing to show. So we can do both sensing and communication at the same time. And
we are showing a demo of our integrated sensing and communication system. Our ISAC system can successfully sense the target activities and also transmit the data
where you can see
wirelessly
that we are
using the same channel.
transmitting the
demo
activity,
setup
which is the video in parallel,
which is used to send
which is basically joint sensing and communication at the same time.
also attached with
There is a camera, there is the
video.
sensing.
We are showing a demo of our.
So last but not least, one thing we are doing is integration of Open RAN with RIS for a remote dentistry application. The idea here is that we have developed our own Open RAN testbed. And the idea is that can we control a robotic arm, which is UE in this case, where we have basically an X app developed in a rig. And also we have a small language model here. And the idea is that by using this, if there is a blockage between the transmitter and the receiver, which is this robotic arm, there is no direct path. We use RIS as an interface to continue our connectivity. And the key here is our small language model, which we have implemented in our rig controller. This is basically helping to automatically configure our RIS to develop a link for robotic arm with the network. So I was thinking what to put as a summary. The key is that future is already here and we all need to work together to make it happen. We have so much literature outside about whatever I have talked, which you can find. And I would like to say that this all work is not done by me. It is done by my colleagues, students in a collaborative way. So I would like to thank, first of all of my students, postdocs, colleagues, and funders, which help us to achieve all the work which I have presented. So that's why I believe that success is a group achievement. So thank you very much for listening. I'm open to all the Q&As, and I'm really sorry once again for a glitch. WebEx, I have been told it was probably because there were so users who were attending. So thank you for listening.
Thank you, sir. Thank you so much. And I will take the questions from the chat box and will repeat to you. You can answer the question, sir.
Sure.
Sir, which machine learning algorithm is used to calculate the pattern prediction of RIS?
So the key here is that we are currently giving the parameters in a manual way. So we are using a PSO algorithm where we are looking at receive signal strength, and based on that, we give the configuration. But the future work which we are doing is basically, which I just mentioned, that we are working on language models, which is basically generative AI. And the idea is that it automatically computes the parameters and give as an input.
Thank you, sir. I'm just moving to the next question. What is the maximum phase shift ranging a unit cell can achieve, and how does it impact beam steering?
Sorry, what is the question? Could you please repeat?
What is the maximum phase shifting range a unit cell can achieve, and how does it impact beam steering?
Oh, okay. Basically, shifting range of a unit cell is based on the design of the unit cell. So we have scenarios where you can have a continuous phase shift as well. So there is no limit on that. You can do the phase shift control by controlling the unit cell. But the key is cost and efficiency. So that needs to be considered. Yeah, next.
Thank you, sir. I'm just moving to the next question. How does the physical size of an unit cell affect its ability to steer beam effectively? Physical size
How
of
does the physical size of unit cell affect its ability to steer beam effectively? So, again, this is a trade-off. So, if we have a larger physical size, we have a more ability to control the beam. But it's a trade-off. If we make a unit cell which is of a size of a room, then it does not make sense, right? So it's a trade-off between the cost and beam steerability linked to physical size.
Just moving to the last question for the time being. What is the relation between the operating frequency and the beam steering capability of a single unit cell?
Operating frequency and the beam steering capability. I think there is no direct relation between operating frequency and beam steering capability, because beam steering is controlled by the configuration, and operating frequency is linked to the size of the unit cell. So there is no direct link.
Okay, sir. For time being, we just stop the questions. Swarnima, you can hand over the session.
Thank you so much, Professor. We appreciate your efforts and adjusting your time according to the session timings. We are grateful for your contribution for today's session. Thank you so much, Professor, for joining in. Moving on.
Yeah.
Yes, sir. Thank you so much, sir, for joining us, sir.
Thank you.
Sir, thank you so much, sir. So, in spite of busy with the Christmas celebration, you agreed our invitation and delivered a wonderful lecture. So, thank you so much, sir. We'll keep in touch. I will contact you
Thank you
later.
once again for the invitation. And any question, please drop me an email. I know we do not have enough time. Thank you. Bye-bye.
Yes, sir. Thank you, sir. Bye, sir.